AI image and video models are hitting a new phase. They're getting faster, more deployable, and more flexible without giving up quality. One result shows how a compact student can now learn from much larger modern diffusion teachers even when their latent spaces don't match. Another shows a single video model that can switch between bidirectional and autoregressive generation at test time. And a third shows you can cut diffusion costs dramatically with stage sampling without retraining the model. Let's explore the first paper. Cross-space distillation teaching one-step students with modern diffusion teachers. Cross-space distillation from Qualcomm AI Research with collaborators at the University of Wisconsin-Madison, Johns Hopkins University, and Rutgers University. Reframes one-step diffusion distillation for the real deployment case where teacher and student do not share a latent space. The paper shows that modern teachers such as Stable Diffusion 3.5 Flux, 2 Klein, 4B, SDXL, Colors, and PixRCs can be distilled into compact Stable Diffusion 1.5 and SD 2.1 students. Despite a 1024 times 1000 and 24 teacher to 5, 12 times 512 student resolution gap, and mismatched VAE parameterizations. The key module, Bridge, is a lightweight 5M parameter latent interface that reuses a frozen prefix of the student decoder as a spatial prior and learns a SWIN IR projection head trained with L1 latent reconstruction and an attention fidelity loss using reverse KL on teacher self-attention. Across 5 teachers, the SD 1.5 student improves HBSV3 from 5.37 to 9.42 with SD 3.5 medium, while the merged checkpoint reaches 10.53 HPSV3 and 29.07 HPSV2 without increasing the one-step inference budget. The supplementary report shows Bridge adds only 6.01 milliseconds to 18.01 milliseconds runtime and 0.54 gigabytes to 0.78 gigabytes peak memory, and that a 30% pruned 1.5B baseline is far weaker than the 0.86B Bridge student on HPSV3, HPSV2, image reward, MPS, and DPG bench. The method also supports inference time resolution upgrade, decoding 512 times 512 student outputs into teacher-compatible 1024 times 1024 images. Let's explore the second paper, Flex Forcing towards a unified autoregressive and bidirectional video diffusion model. Flex Forcing, from NVIDIA research with Xingqiao Wang and Arash Vadat among the authors, reframes video diffusion as a single model that can switch at test time between bidirectional and autoregressive generation. Built on WAN2, WAN T2V, WAN 3B, and trained with a WAN 3B teacher. It introduces flexible chunking over both frames and denoising time steps, so early high noise steps can use coarse global chunks, while later steps use finer local chunks. A key technical addition is K-projection, a time-step conditioned key cache alignment that resolves the signal-to-noise mismatch when causal past tokens and non-causal future tokens coexist in attention. On 5-second video generation, the paper reports that flex forcing reaches 85.07 vbench total quality and 86.33 semantic at 25.8 frames per second with 5 denoising steps, while a faster setting reaches 29.4 frames per second at 84.63 total quality and 85.89 semantic. In the 2-step regime, it still attains 84.2 total quality and 85.27 semantic at 24.9 frames per second. For 30-second video on vbench long, it improves total score to 84.01 and raises FPS to 24.96, outperforming self-forcing and infinity rope on long horizon coherence, motion, smoothness, and dynamic degree. The model also enables any order, any step autoregressive editing, allowing localized video edits without regenerating the full sequence, which is a practical step toward controllable long video synthesis. Let's explore the third paper, Multi-Resolution Flow Matching Training Free Diffusion Acceleration via Stage Sampling. Mr. Flow, from Beihang University, ETH Zurich, and collaborators, is a training-free acceleration method for modern flow matching diffusion models such as Flux, OneDev, and Quen Image. Instead of shrinking inference purely in latent space, it uses a staged low to high resolution pipeline. Generate the global structure at low resolution, decode to pixels, apply real ESR-GAN super resolution, re-encode, inject low-strength noise, then perform one high-resolution refinement step. The key idea is that low resolution cuts token costs by 4 times per step and converges in fewer steps because the model spends about 58% of the original trajectory on low-frequency structure, while the high-resolution correction segment is close enough to the clean endpoint that a single Euler step is usually sufficient. On 1024 times 1024 evaluation, Mr. Flow reaches 8.25 times speedup on Flux, 1 dev with 12 plus 1 steps, and 10.3 times on QuenImage with 12, 1 times 2, while keeping 1 IG bench within roughly 1% of native inference. It also composes cleanly with pre-trained time-step distillation. Mr. Flow plus PyFlow reaches 11.3 times on Flux, 1 dev, and 25.1 times on QuenImage. The paper argues that pixel space GAN super resolution is critical because latent space upsampling causes artifacts and blur, whereas low-strength noise selectively resamples high-frequency errors without erasing the preserved low-frequency layout. That's a wrap on today's AI paper highlights. Thanks for watching.